Hey everyone, welcome to another little recap video from Year 9 Trigonometry before we move on to all of the new content that we're doing in this series, which is Year 10 Trigonometry. We are looking now at finding unknown angles. So I'm going to do the same thing that we did before in terms of the setting up the ratios and checking with this trigonometry table I've included at the start of this series. And once again, I'm going to show you how to do this with a calculator too. And right at the end, we're just going to look at an interesting application of trigonometry to linear relationships as well as a little bonus. So what we're going to do, we're just going to go through one question to recap how to find unknown angles on right angle triangles. So I'm going to just draw up a quick right angle triangle here with an angle theta here and 2.5 and 1.5. Okay, so as we've done before, we want to first name all of our sides here. So we have our hypotenuse here, that's kind of constant, it's always opposite my right angle here. And the side here, 1.5, that's next to my angle. So another word for next to is adjacent. We've talked about this before. And our final side is the opposite. So here we have an adjacent and hypotenuse given to us. So the trig ratio that deals with adjacent and hypotenuse is going to be cos. Goes from so, ka, toa, cos deals with the adjacent and the hypotenuse. So if we pop this in, we're going to say that the cos of this angle is going to be equal to the adjacent over the hypotenuse. So here we're looking at 1.5 over 2.5. And we talked about this last year. The way to undo this type of operation is we want to eventually get to theta. So we want to do an inverse operation like we would usually do when solving equations. So an example of an inverse is, for example, if we have x divided by 2 equals 4, the inverse operation would be to note that here x is dividing by 2, so I do the opposite to both sides to solve the equation. Now we do a very similar thing with trigonometry. However, there is some notation that we have to get comfortable with. So if we want to find this, we can have theta on its own on the left hand side, and that is going to equal to the inverse of cos. So we do this thing here, and you may remember from the previous series that we can generate this inverse by doing the shift button and then clicking the type of trig ratio that we have here. So here we're going to do cos there in order to generate this guy here. So this is the inverse cos. My theta equals to the inverse cos of 1.5 over 2.5. And when we put that into our calculator, we are going to get 53.13, etc., which we can also convert to minutes. If we want to find this to the nearest minute, we're going to get 53 degrees and 8 minutes here. Okay, so our calculator just allows us to just do this right off the bat by doing this inverse trig function. But let's just double check this answer on our table just to make sure what we've done is correct. Now, if we put in 1.5 divided by 2.5 into our calculator, finding this trig ratio, that gives us 0.6. So if I wanted to find this guy here on my trig table, I can then match the angle that this gives me. So if I'm looking for cos here, and I want to find the value of just the closest thing here to 0.6, because here these trig ratios are typically irrational numbers. But if we look, I can see 1.6018. So that is going to give us roughly 53 here. Now, it's not going to be to the same level of accuracy that our calculator gave us, but we can confirm that, in fact, based on our table 2, this gives us around 53 here as an angle. Okay, now let's look at, we've covered how to do this for finding angles. Now, this is going to be the same every single time. We're going to find these sides, set up our equation here by picking first the trig ratio based on the sides we're given, and then we can take the inverse trig function. We take the inverse trig of that ratio in order to find the angle theta. Now, if you want more examples, I covered this in year 9 as well, but we're just going to talk about one interesting application of trig in linear relationships. So let's just draw up an XY grid here, and I have any random line, y equals to mx plus b. Okay, so if I want to find the gradient, typically before we would say, okay, we have our rise over our run. So we would see, for example, between this point and this point, we would find how much the graph went up, so how much it rose, for how much it ran along the x-axis in the positive x direction. So we have our rise over run. So our m equals to rise over run. Now, interestingly enough, what I've just sketched out here, let's look at what shape this actually makes. So between the actual line, its rise, and its run, we construct a right angle triangle, because any vertical part on my grid is going to be perpendicular to my horizontal part. This is because our axes meet at 90 degrees. So any horizontal line we draw is going to be perpendicular to any vertical line we draw. Okay, so now that we have this, let's just consider something interesting here. So I've got this, and for example, I've got some angle theta here, because my line is going to make an angle with my x-axis, with my horizontal axis here. So let's actually look at something with trig here. So say this was a right angle triangle. I have an angle here, and I want to name all of my sides. So I have a hypotenuse here opposite the right angle. I have an opposite side to the angle, and I have an adjacent side to the angle. So if I wanted to set up a trig ratio with this, I've been given the adjacent and the opposite. So looking back to SOHCAHTOA, I am looking at my tan here. That links the opposite to the adjacent. So I can say that tan theta equals to my opposite over my adjacent, which is my rise over run. And my rise over run is just given by m, the symbol for the gradient. So another way I can define my gradient is by doing tan theta. Because anytime we measure the rise or the run, we're constructing a right angle triangle. And the angle that this line and my axis make, that angle theta, we can use that angle and model what the gradient will be based on a trig ratio. So we'll come across this a little bit later, not as much now, but this is just a really interesting idea that comes out when we apply trigonometry to linear relationships, which we've done in the past.